In the last video we saw that, in general, the continuous version of the Shannon entropy is not coordinate independent. This is a problem in physics, as only objects that are coordinate independent can have a truly fundamental status. By coordinate independent we mean that their definition does not depend on the choice of coordinates or any other arbitrary choice. The short story is that, while the Shannon entropy is not in general coordinate independent on continuous spaces, it is over physical spaces. Let's first look at classical phase space. Here we have conjugate pairs of q and p, position and momentum. The idea is that if you change the position coordinates q to q hat, p hat will change in a way that minus rho log rho is invariant. In fact, phase space has exactly the structure one needs to define coordinate-independent distribution with an invariant entropy, meaning all distributions are invariant over phase space, and if you wanted a manifold over which you can define invariant distributions, you get phase space. For those interested in the details, I'll leave a link in the description of a paper that goes into the details. Here we are interested only in the first part, the distribution over phase space are invariant. What does that mean? Well, we have our state variables, position and momentum. We change coordinates, which means we change the state variables for position q to q hat according to some arbitrary but invertible function. The momentum also changes and the components change covariantly. That is, we have p hat lower j equal derivative of qk with respect of q hat j times pk. The lower indices are there to remind ourselves that the q hat j is in the bottom. Now we calculate the Jacobian determinant. The Jacobian matrix is the derivative of the new variables with respect to the old variables. So we have a block matrix with all four combinations. Partial q hat partial q is arbitrary, so we can't say any more about it. Partial q hat partial p is 0 because the new coordinates only depend on the old coordinates and not on momentum. The second row is essentially the derivative of this expression, and note that the first factor is only a function of q, while the second factor is only a function of p. So partial p hat over q gives us mixed derivative of qk by qi and qj times pk, while partial p hat over p is partial qk partial q hat j times the identity matrix. Since the matrix is block diagonal, the determinant is this times this minus this times this. But this is 0, so the determinant of the whole is just the determinant of partial q hat partial q times the determinant of partial q hat. But this is the inverse matrix of this, so the determinant is reciprocal and the product is 1. Now recall the general transformation for the density. The new density is the old density times the Jacobian determinant, which is 1, so the density is invariant. The entropy is the old entropy minus the expectation of the log of the Jacobian. But the Jacobian is 1 everywhere, the log is 0, so the entropy is invariant. On phase space, densities and entropies are invariant. This, I think, is what most people miss about classical mechanics. Invariant densities and entropies are the fundamental property of classical phase space. Often people say that the Liouville's theorem, the idea that the entropy of areas of phase space are conserved in time under Hamiltonian evolution, is what gives entropy a special status. I think that misses the point. It is the fact that entropy is the same for all observers that enables us to talk about entropy in the first place. If all observers didn't agree on the value of entropy in the first place, on whether two distributions have the same entropy or not, how could we even discuss whether it is or is not increasing over time? Also, note that the densities too are invariant over phase space. This is why we should always do statistical mechanics in phase space, with position and conjugate momentum and not with position and velocity or kinetic momentum. It is only on phase space that you can compare densities for two different states in a way that is meaningful. Now, in general, entropy can decrease or increase over time. Hamiltonian evolution represents deterministic and reversible evolution, the case where entropy and densities stay the same. One possible source of confusion is that by coordinate we mean the spatial coordinates qi only, not the unified coordinates of the set of all variables q and p. You can in fact make an arbitrary transformation of state variables that will distort densities and entropy. These correspond to non-canonical variables. The point is that if we change coordinates qi, there is only one change of pi, the covariant change, that results in canonical coordinates. That is why pi change covariantly. Entropy is also invariant when applied to quantum mechanics as the von Neumann entropy. Suppose you have a density matrix. Eta represents a set of eigenstates, and rho eta is the density associated to each eigenstate. The Shannon entropy is the expectation of a self-information minus log rho, as we saw in the second video. This is minus the trace of rho log rho, the von Neumann entropy, which is minus rho eta log rho eta. So the von Neumann entropy gives us the Shannon entropy. Now suppose U is a unitary transformation, and a coordinate transformation is a unitary transformation. The transformed density matrix is U rho U dagger. So the von Neumann entropy is minus the trace of U rho U dagger log of U rho U dagger. Since U is invertible, U and U dagger go out of the log. U dagger U is 1, so we cancel it out. The trace is invariant under cyclic permutation, so U dagger can be brought at the beginning and cancels out. So the entropy of U rho U dagger is equal to the entropy of rho. The entropy is invariant under coordinate transformation. To sum up, the continuous version of classical entropy is in general coordinate dependent, but the structure of classical phase space and of quantum Hilbert spaces make it invariant. It's the physics embedded in these special spaces that makes the Shannon entropy an objective physical quantity. This is precisely why we have these spaces. We would not be able to do physics if they didn't have that property.